There we go. All right, chapter 11 is the last thing we're going to be doing this year. Okay, so the title of the chapter says Modern Atomic Theory. Now, I want you to think back in the first semester. Do you remember the chapter we did, the grid game, and we talked about protons and neutrons and electrons? Does everybody remember that or not? Okay, we're going to take this idea much further, okay? What I was teaching you would be the same thing I would teach in the first semester. I would even teach it in middle school. If I were teaching middle school chemistry, I would teach that same thing about protons, neutrons, electrons. I probably wouldn't teach this to a 7th grader. Elementary kids, don't they know what a nucleus is? And maybe protons? They knew something like that, don't they? You would never teach an elementary student this. It wouldn't make sense to them. But you guys are in the 10th grade. Got it? You've got to tell yourself, I'm a 10th grader. I should be able to be capable of doing a lot. I was very fortunate to, I got invited, but last night, I was at High Point University. And we had a former student of mine. She took chemistry. She also took advanced chemistry. And I can tell you right now, she wasn't the A student. She wasn't the A student, but she worked hard. When I looked at her notes, I have never, in all my life, I've never seen a student who had those kind of detailed notes. So I knew that she eventually could do a lot. She ended up going to High Point University and majoring in chemistry. And not only did she do really well, she started tutoring, and they paid her to tutor chemistry. So even though she didn't do great grade-wise at the beginning for me, all right, she'd usually get B's or C's. She went on, and she had these great notes, and she had she wanted a desire to learn. And she goes there. Not only does she tutor in chemistry, she gets her degree, and then they have a pharmacy school there. And that's what I went to last night. She's now a doctor of pharmacy, so she is going to be a pharmacist. Excuse me. The only reason I want to tell you that is that you might think grades are everything. I want you to think about what are you learning? Are you learning things? Are you learning tools? Are there tools to help you learn better? Can you learn something about yourself? You know, I don't do very well when I wait till the last minute and try to study for a test. Can you learn that about yourself? Or I don't want to do a planner. I saw other people doing a planner. I'm not doing a planner because I'm real prideful. Have you ever thought about maybe if you had a planner and you made yourself do it, for 2 weeks, it might become a habit? So, all right, I want you to say, I just want to learn. I want to learn this material. When I first say some things, it might not make sense. Just stay with me, all right? Well, first of all, it says the modern atomic theory, and I want to mention to you that, do you have a guess as when the modern atomic theory was first proposed? Anybody want to take a guess? Was it like last year? How about 10 years ago? Well, how about 20? Anyway, it's not going to sound right to you, but the modern atomic theory started in the late 1800s and the early 1900s. In the late 1800s, something happened. A group of people found that there were these materials on the planet that seemed to give off energy. And as a matter of fact, they could hurt you. And they were called radioactive. Have you ever heard of anything radioactive? Okay, like you watch The Simpsons or something like that. Anyway, and they said, what is happening here? This rock that looks like a regular rock, if I put it in a chamber with a mouse, the mouse is dead in 30 minutes. What's going on here? When I put this rock in a dark room with a piece of photographic film, you don't know what that is because not everything you have is digital, a piece of film, it makes the film expose like as if somebody shined a light on it, but I didn't. What is this stuff that's called radioactive material? And so a group of people started studying this and said, what's happening down there at this level? And then in the early 1900s, there was one of the biggest explosion of physics people ever in the whole world. And you ever heard of Einstein? Einstein's a person. Schrodinger, he's in this chapter too. Niels Bohr. All these people started investigating the atom. And they said, if we could find out what the atom's really made of, really the details of the atom, it'll open up a whole nother branch of science, and we might find out things we've never known before. Are you with me this? So the modern atomic theory is probably finished at around 1930. You're talking about almost 100 years ago. And yet, so far, everything they said has come out to be true. So what I'm going to do is show you what we're going to be doing here. In this chapter, I have to show you a little bit of thing called physics. Physics is kind of like the way things work. It might have to do with light or sound or motion. That's what gravity, that's physics stuff, okay? So we do a little bit of physics of light, and then we're going to talk about what happens to an atom if you excite it. If you get it excited, what do electrons do? Next, there's about 6 scientists in this chapter. We're going to talk about them. What did they do to make this theory happen? And then here's what I spend a lot of time on. This is called the electron configuration. I remember when I was young, and the first time I ever heard that word, I said, there's no way I've ever heard that word before. And yet, let me tell you what it means. The configuration of my tables in this room is different than the configuration of tables in Miss Found's room. What do you think I mean by configuration of tables? What is it? The order, the way they're arranged, right? The order, the way they're arranged here is different than the way she arranged her tables. And so electron configuration is nothing more than helium, how do you arrange your electrons? And oxygen, how do you arrange your electrons? That's all it is. And it's that arrangement of electrons and what happens when you excite them, that's what this chapter is mainly about. Now, another thing that goes along with it is you should be able to look at the periodic table and tell me how the electrons are arranged. The periodic table has this weird shape because it's the way electrons are arranged. So this is an intro, right? Have you ever gone to, you've probably never gone to something like a theater. Have you ever gone to a Broadway show or anything like that? Any kind of, okay, when you see a Broadway show, the orchestra plays an overture. You know what that is? What are they doing when they're playing they play, like if you went to see Les Mis, you would hear them play, before the play even started, a little bit of this song, a little bit of this famous song, and it'd be a bunch of those that give a whole overview of what you're going to hear during the play, during the musical. So what I just laid out in front of you was the overture. It's like, here's what's happening in the whole chapter. Now, it's time for the play to start. Now, the first thing we're going to look at is this. I can't teach you this chapter unless you know a little bit about light. And if you understand about light, they always have pictures of waves. Okay. Now, be honest with me. Do you remember anywhere in middle school or 9th grade, did you do study waves? Yeah, like waves, did you ever hear the word wavelength in any of your classes? You did? Okay, did your teacher say the top of a wave is called a crest? Did anybody tell you that? And the bottom's a trough? Have you heard that? Okay. Now, the distance between one wavelength, like the crest to the next crest, that's called a wavelength. Now, what I want to show you in one of my demonstrations, I'm going to start that in just a minute. You need to know a little bit about these two words here. The distance between the crest and the crest is a wavelength. I could even go trough to trough, and it'd be the same distance. And some waves have long wavelengths, and some have shorter. That makes sense. Now imagine a wave that had a really long wavelength, and I was at the beach, and I watched a really long wavelength, and I watched to see how often it hit a pole, like the maybe a pole that was in the water from the pier. And I watched it and I say, ready? Splash, splash. How often the wave hits the pole is called frequency. Frequency is how many waves per second, how many waves per minute are going to hit. So imagine you have a really, really long wavelength. How frequently will that wave hit the pole? You say, well, not that often. But what if you had a bunch of really small waves? Wavelength was tiny. Then how often would it hit the pole? It would be more frequent, wouldn't it? So here's the first thing I want you to know. If a wave has a long wavelength, it has a low frequency. It doesn't happen very often. If it has a short wavelength, what happens? It happens many times per second, doesn't it? It has a high frequency. So a little bit of physics here, okay? I'm gonna do a. I'm gonna go ahead and get a model out here. I have the Slinky I have is not like the Slinky you can buy at a toy store. This is one that you can get in a science catalog. So what I'm gonna do first of all is, and what you do is grab hold of this and don't let go of it, and go all the way down to that bar as far as you can that way. And don't let go of it. You can hang on, grab it. You just grab it. Go all the way down. Keep going. Keep going. All right, there you go. Now lay down on the floor, but don't let go of it. All right, now if you guys want to stand up, can you see from there? Okay, so what I did, I have a Slinky, and what I'm going to do is I'm going to make a wave. Okay, and I want you to, when I make a wave, I want you to look to see if you can see a wavelength. Okay. Now, can you see the top of one wave and the top of the next wave? That's a kind of a long wavelength. I'm going to try to make a short wavelength. What do you think about that? I can try to make a shorter wavelength like that. Now, what's interesting is I have, let's see if I can find it. Here it is. Can you see a little piece of paper, a little piece of tape right about here in that green, see the green block right in front of me? There's a little piece of tape there. Now, why would I put a piece of tape on there? I'll show you why. Most people think that when they see this, it looks like a piece of Slinky from down here went all the way down to there and came back. Now, watch that piece of tape though. If the real piece of Slinky went down there, wouldn't the tape have gone with it? So my question for you is, what is it that went down there? What went down there? It wasn't Slinky. So what do you think? Give a guess. Daniel, what do you think? What traveled? All right, lay down again. What traveled? So it's called a wave, but what's traveling? What's traveling along the way?
Gravity.
It's not Slinky. All right, not gravity. What do you think? Watch. What went all the way down and came back? What do you think? Come on. Yes? What do you think?
Frequency.
What is it?
Frequency.
Frequency is how often a wave would occur, right? How often? I can make high frequency. What? High frequency, ready? That's many, many waves per second, like that. See that? Here's low frequency. See that? So what's actually traveling though? Starts with an E. Energy. Okay, now, if you ever do get a Slinky like this, and you'll get a long one like that, but you can still do some play with it. There's another kind of wave I can make, which has nothing to do with this chapter, but I'll show it to you anyway. Watch what happens when I do this. I'm going to pull some of these back and let go of it. You see how it goes? That goes down better. That's pretty neat. All right, ready? On three, we'll let go. 1, 2, 3. That's fine. So, one thing that you probably aren't going to like is, I'm going to talk about the beach a little bit and say, I like the beach, but here's something you think you knew, but you didn't. you're standing ankle deep water and you see a wave out there. You said, well, how long is that? In a while, that water out there is going to come and splash on my leg. And it does come here and it splashes on your leg, right? That's not true at all. That water that was out there that you looked at, you pointed to, that water did not splash your leg. If you were to put some dye in that water and you watch it, the water would go up and down, up and down. None of that water came all the way to the beach. You don't like that. Yet you knew that a piece of slinky didn't really go from my hand down there, did it? How could a piece of slinky come disattached? A piece of slinky did not go all the way down there and come back. But what did go down there was the energy. Energy went through the slinky and came back. And when you see waves come in the ocean, that water is not coming to you. It is not. The energy is traveling through the wave and hitting a particle, hitting the next particle, hitting the next one, and you see a wave, but the water is not traveling. It's the energy traveling in it. So the water that's always been behind, down there by your ankles, that's the water that gets splashed up to your knees. It's the same water. Over and over gets splashed on your knees. Oh, no, that's not right. That's not right. Okay, don't believe me. But when I see a seagull or a pelican, and they're floating there, right? And here comes a wave. What does the pelican do? If the water actually moved, then the pelican would come toward me, wouldn't it? What's the pelican do? Doesn't it? The water does not travel from out there into here. The energy travels through the wave. Yes?
How does stuff get washed up on the beach?
Okay, so if the water's deep enough, and let's say the wavelength goes down this far, and the bottom of the ocean's here, well, then the wave will keep coming. It'll keep coming. But then, when the water gets this shallow, and the wave tries to make a full wavelength, it'll run to the bottom, won't it? When it runs to the bottom, that's when it starts splashing water up. So when the water is deep enough for the wave to complete itself, it'll just keep traveling. But when it hits that place that's too shallow, it'll go whoosh, and it'll splash it up in your leg. Sometimes it splashes before it gets to your leg, doesn't it? If it's a big enough wave and it gets shallow out there, it'll crash there and then come to my leg. All right, now the reason I want to show this to you is that anytime you want to study energy, especially things like light energy, it travels in waves. And so we need to know what waves are. But I do want to tell you, the waves we're going to study right now are actually a little different. Light travels in waves. But it doesn't have to go through water. It doesn't go through air. It can go through nothing. Every wave you've heard of in your lifetime. Here's another one. I'll make another one. Here's a wave. I'm going to take this ruler and go like this. Sort of. Now, what I'm doing is, when I do that, it vibrates the air, and the air goes like this, ba-boom, 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 like that. And when that wave hits your eardrum, it makes your eardrum go, ba-bam, ba-bam, ba-bam. And then your brain says, a sound. And so this kind of energy, sound energy, it has to travel through air. You've probably done this before. You put your head on a table, and then, you ever done that? Put your ear on the table and tap the table with your finger. Do you hear it? So that energy is actually traveling through the table, and that energy needs a material to travel through. Light is more interesting than that. Light can travel through nothing. It can travel through nothing. And that's called electromagnetic radiation. Whenever, one thing that helped me a great deal in science, the first time I ever saw the word electromagnetic radiation, I said, I have no idea what that was. If you just say the word light, then you substitute the word light. The electromagnetic radiation, you mean light? Yeah, just say the word light. Now, God made light. This is kind of interesting, I think. He made light, but he made more than one kind of light. And so what I want you to see right here is, see these numbers right here? at the top, the numbers show the wavelength in meters. So can everybody look up here? Now, look over here, and you see where it says 10 to the fourth? That's 10,000 meter sticks. Here's a meter stick, right? The top of one wave and the top of the next wave, 10,000 meters that way. That is a long, long wavelength, isn't it? Now, those are called radio waves. Now, when I was your age, I used to think radio waves meant like sound. No. Sound waves might travel at 800 miles per hour, maybe 600. Light travels at the speed of light. Do you have any idea how fast that is? 800 miles an hour is fast. 600 miles an hour is fast, right? The speed of light is like 186,000, right here. The speed of light is 186,000 miles per what? If it was per hour, I think that was fast. No, every second. It travels that many thousands of miles every second. Light can go around the earth 7.5 times in 1 second. If you had a fiber optics, and you said, turn the light on, 1001, it would have gone around the earth 7.5 times and come out. Light, they have a special mirror on the moon, and whatever light shines to it, comes right back at you. And we fire laser beams at the moon, and they come back at us, and we have atomic clocks that measure how long it took. It takes a little over 3 seconds to go to the moon and back at the speed of light. Anybody have an idea how long it takes light from the sun to get to the earth?
8.
You're right. How did you know that? That's excellent. It's about 8.3 minutes. It takes a little over 8 minutes for the light from the sun to get to the earth. What does that mean? You must be really far away. It only took 3 seconds to go to the moon and back. You're telling me it takes more than 8 minutes for the light from the sun at traveling at the speed of light? So God said, I'm going to have one kind of light that has a really, really long wavelength. It's called a radio wave. Now, a radio wave does not sound. It does not sound. What do radio stations do? They send out light. They send out radio waves. But on that wave is a code. They have embedded a code on that wave. And when that code hits my radio, the radio takes the code and decodes it and tells the speaker, boo, 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 boo. The radio station does not send sound, it sends light. And the light is the signal on the light is changed into sound. When we talk to astronauts, if astronauts are on the moon, hey, how you doing up there? How could we talk to them? There's no wire. There's no cell phone service that goes all the way to the moon. But they can send their signal at the speed of light back to NASA. And it still takes about 2.5 seconds to get there. And they can talk to them at the speed of light. So this is called a radio wave, but it's really a form of light. And can your eyes see this? Can you see? There's radio waves right now in this room. I can't see them. Let's go down here. How about microwaves? When you turn on the microwave and look in there, do you see any colors? They're there. But my eye, I can't perceive that wavelength either. Let's go on down. Infrared. I can't see that either. Here's what's God's kind of interesting. God said, of all the forms of light, I'm going to let your eyes perceive a little sliver. A little sliver of light is the only thing you're going to be able to perceive. When I look around the room right now, everything that I can see, everything, has to fall in the between 400 and 700 nanometers on a wavelength. I can't see light unless it's between 400 and 700 nanometers. And this is called Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Have you heard that before? Like when you see a rainbow, this is the order. So of all the kinds of light, you can only see not the entire electromagnetic spectrum of light, you can see the visible spectrum. Now, when I do a demonstration on Monday, I'm going to show you that white light, when you look at white light, it really has red, orange, yellow, green, blue, violet in it. It's really there. It's been all those different wavelengths hit your eye at the same time. You say, oh, that's white light. Look at this. Oh, white, it's white. No, that's not, you know why it's white? Because all of Roy G. Biv is hitting your eye at the same time. You know why it's black? Because the chemicals here are absorbing all of the Roy G. Biv. And what's left over? Nothing. I see black because light doesn't reflect. Look at this. Why is that green? Roy G. Biv's hitting it? What's the only color that this dye does not reflect? I'm sorry, what's the only one that it won't absorb? Green. It doesn't like green, so it reflects green. If you take a plant and you grow it in only green light, you'll kill it. Because what do green leaves do to light? What does leaves do? They absorb almost every kind of light except what? And they reflect green. So things are green not because they absorb green, because they don't absorb green. Now, let's go down here. Can my eyes perceive these smaller wavelengths? Yeah, how about ultraviolet? No, I can't. They have experiments that they've done. I know you're not going to like this, but they've actually taken bees' heads and hooked up cameras into their eye. And they know that bees can actually see ultraviolet, but you can't. Now, we can make a camera that whenever ultraviolet hits it, it makes a visible image so my eyes can see it. And they have an infrared camera, an ultraviolet camera. And so we actually know that bees can see in the ultraviolet range. I cannot. So I've seen some films where they show a regular field of yellow flowers, you know, it look kind of boring. And then you look at it with the ultraviolet, and like the flowers, the yellow flowers have little arrows going, hey, want some nectar? Huh? Huh? And it's like they're pointing to where you get the nectar. I didn't see that, but the bees see it. Let's go on down. How about X-rays? Did you know X-rays were light? And how about gamma rays? Light. Now, I think it was Layla. You said that when the wavelengths were really long, how often would a wave come by? Very frequent or not very frequent? You're right. Listen to this. This is the one thing you have to remember. Long wavelengths have small frequencies. Now, go over here. How about somebody that has really tiny wavelengths, like gamma rays? Tiny wavelengths have high frequencies. They occur very often. Now, one more thing. Hey, I don't want to take your phone, okay? Just put it up. What you need to know, if you have high frequency, you're high energy. So let's try it one more time. Right there. See those guys? Gamma rays? Small wavelengths, high frequency. High frequency, high what? High what? Energy. Now, so guess what? If I said, stay right there, I'm going to hit you with 1 minute of radio wave light. And then I say, stay right there, I'm going to hit you with 1 minute of gamma ray light. One of them is going to hurt you a lot. Which one? Which one is a high energy light? What do you think? Isabel, I haven't called you yet, sorry. Which one's high energy? One more time. Small wavelength means high frequency. High frequency means high energy. Which one of these lights would hurt you more? Gamma rays or radio waves? Gamma. Gamma and X-rays, you don't want to be exposed a long time to those. They're high energy forms of light. Okay, now let's go down here, and I'm go to the next part of this chapter. Way back, even in the 1700s, there's a guy. There's no way. I don't see how you could be alive and have not have heard about Isaac Newton. Have you heard about Isaac Newton? Well, I guess I'm not alive. But Isaac Newton is probably one of the, except for Einstein, probably one of the most famous scientists, right? Yes. Okay. Now, even back then, in Isaac Newton's time, he studied light. And he got really famous studying lenses and mirrors and light. And there's a really, really famous painting of him. If you could find that, that would be neat to have that. I might give you extra credit. But you won't find the real painting. But I meant like maybe a reproduction or something that didn't cost very much. So here's Isaac Newton in this kind of it's a sunny day, but he's got the curtains are drawn. But he has a little piece of the curtain cut out. And it means one really strong sunbeam is coming into the room. And then he has this piece of glass in his hand that looks like a triangle. Have you guys ever done anything like that in middle school? What do you call that little triangular piece of glass? Prism. And what he does, this famous painting, it has the white light from the sun hitting the prism. And then shining on the wall is a rainbow. Roy G. Biv. And before Newton, people did not believe that. They still didn't believe after he showed them. He said, white light's really made of many kinds of light hitting your eye at the same time. The prism would make the light bend. Did you ever use the word, you're pretty sharp on this. You ever use the word refraction? Reflection means to bounce off, right? Refraction means to bend. You're here and you bend. Okay? If you refract light enough, it'll separate it into colors. That's called diffraction. Okay, so now, let me tell you what happened, okay? Everybody said, Newton, come on. You know that piece of glass has something in it, and it simply colored the light. White light's not made of those. You color the light. So then he did another experiment. He put the prism there and made a rainbow, like on his hand. He took another prism, turned it upside down. And then Roy G. Biv hit the prism, and guess what? It all went back into white light. There's no way, if it was coloring the light, that it would turn back into white light. So he proved that light really was made of all those colors in your eye at the same time. Now, back in Newton's day, there was a big argument. Is light made of little particles? Or is it like that slinky? Is light an energy that travels through something? Is light a wave, or is light a particle? So which one is it? What do you think happened down in the 1700s? What was the answer back in the 1700s? Anybody know? Some people showed experiments that it had to be a wave. Other people did experiments that said it has to be a particle. So they didn't know. 1800s, they didn't know. It was both. And so guess what the modern theory is that light is both. It's called the dual nature of light. It acts like a particle and it acts like a wave at the same time. So let me show you what's happening here. In the modern world of light, here's what we think light is made of. We think light does travel in wavelengths, in waves. We think it travels in waves, but the little particles have a name to them. Do you remember, has anybody, I'll show you in here, I want you to read this chapter, but what is the name of the little bundles of energy that act like a particle that light travels in? Has anybody ever heard that word before? Hey, May, gotta put your head up, okay? It's traveling in a wave, but that little bundle of energy acts like a particle. What do you call that little bundle of energy that is like the particle nature of light? It starts with a PH. Photon. A photon is that little bundle of energy that's traveling like a wave that when you turn a flashlight on, that's what's happening. Now look right here and see if this makes sense to you. If you had red light, if you looked at red light, it would be made of photons. And each photon would have a certain amount of energy in it, wouldn't it? Now let's look at blue light. Look at blue light. Would it be made of photons? Yes. But tell me how much energy would be in a blue photon. How much energy would be in a blue photon compared to a red? Higher, because remember, blue has a smaller wavelength, doesn't it? So it would have a higher energy. So a photon of blue light has more energy than a photon of red light. That's the modern theory about light. Now, the reason you have to know that, the reason I had to give you a little physics lesson about light is because the experiments that were done that have to do with chemistry are coming up. All right, so let's try. I did this, I think. I may have done this in your class. I think I did. I think when we were doing that, remember those 7 experiments you did? And then I gave a review day. Didn't I put some things in a flame and made different colors? Did we do that? Okay, here's the theory. The theory is when I put lithium in there, the electrons are already in a location. When I put it in the burner, the electrons absorb energy and jump. They jump to a higher level, and then they jump back down, and they absorb energy, release. Absorb, release, absorb. If those electrons release energy in a wave, and it happens to be between 400 and 700 nanometers, what do I see? Starts with the letter C. What do I see? Starts with C-O, color. When you saw that flame test, that was telling them that the electrons were absorbing energy, releasing, absorbing, releasing, and one kind of element, like lithium, would give off this color. But another one, like copper, it would give off this color flame. And this one here was sodium. Now, why would they give off different colors? Because their electrons are already in a different arrangement, configuration. And so if they're in a different arrangement and you start exciting them, they'll give off different kinds of light. The demonstration on Monday, I'm not going to do it today. I'll show you a tube of hydrogen gas. And you know what it's going to look like? Air. It's going to look like nothing. Hydrogen looks like air. But I'm going to put it in a machine, and I'm going to put electricity through it. I'm going to run electricity through it, and I'm going to excite the electrons. And it's going to start glowing. And you'll see a color. Have you ever been to Krispy Kreme or a pizza place, and you saw those really bright orange lights like Hot and Now? You know, what's the name of those? What are those called? Or if you go to Las Vegas to see them all over the place, what are they called? Neon. You know what? I have a neon tube. Guess what neon looks like? Air. It looks like nothing. But when I run electricity through it, it's going to excite the electrons like this, and it's going to give that orange-red light. Now, I'm also going to do on Monday, when you see the orange-red light with your eyes, I'm going to be like Isaac Newton. I'm going to give you like a prism-like thing, and you're going to look at that orange-red light, and you're going to say, what? The orange-red light on the Krispy Kreme donut sign is really made of a green and a red and an orange and a yellow, and there's a purple in there? Yeah. When all those hit your eye at the same time, it looks like orange-red. And so you can actually identify an element by exciting its electrons. And every element has a different set of these. Let me show you what happens. Now, stay with me. This is the highest level stuff I'm going to show you, okay? You can do it, though. You can do it. Okay. See these? What's going to happen is when I show you a bright white light, you'll see the entire rainbow. Everything. No gaps, no nothing. But when I excite a certain element, you won't see a whole rainbow. You'll see, they call them bright lines. You'll see bright lines like this. And when I do hydrogen, you'll see a different series of bright lines than you will for neon. Now, what does that mean? What does that mean to scientists? They said, something's going on here. Your electrons must be in different arrangements to give us different colors. And here's what they think is happening. I got about 3 minutes, and this is some good stuff, but this is probably the highest level thing I'm going to tell you today, okay? Now watch what's going to happen here. Imagine you're an electron of hydrogen, and you're in a normal energy level. You're like, whatever you're doing, that's your normal amount of energy, and that's called the ground state. I told the other class a joke, and some of them got it, some didn't. How is a hydrogen electron where it normally is like hamburger? How is a hydrogen's electron in it where it normally is found like hamburger? Anybody know that? They're both in their ground state. Okay, So anyway, if you take an electron in its ground state where it's normally found, and if you excite it, it will jump to another level. Now you won't see anything when it jumps and absorbs energy, but then it goes back where it belongs and it gives off energy. And what's going to happen is when it might jump down to here, it might jump here, it might jump here, it might jump here. When it makes those jumps, it gives off different colors of light. And every element on the periodic table will give you a different set of bright lines when you excite their electrons. For a long time, if somebody said, I discovered a new element, well, what's this mass? What's this? And then they do one of these. And if it gave the same bright lines as another element already, no, sorry, it's not a new element. But if it was new, they say, all right, you get to name it, you discovered it. Hey, do me a favor, this weekend, if you could either, if you want to read like the first 7 pages here, the story I just told, it'll all come together to you. Okay, hey, have a nice weekend. Don't forget, it is Mother's Day. Do not forget that, okay? It's Mother's Day.